Hello, everyone, and welcome back to another Quantum Mike Classic. We are taking up another old interview that I did back during the COVID times when I tried to run the Quantum Mike as a podcast. This is an interview with Dr. Robert Collister, where we talk about his work on barium tagging for the nEXO experiment. Now, this is back in 2022, so it is a little bit old, but please enjoy. It's a very good episode. Hello, everybody. Welcome back to the Quantum Mic. As always, I'm your host, Owen Dara, and today we are joined by Dr. Robert Collister, a postdoctoral researcher at Carleton University. Thank you for joining me today, Rob.
Hi, Owen. Happy to be here.
Awesome. So, as usual, as we do on the show, how about you introduce yourself a bit more to our guests and listeners so they know a bit more about you and what you do?
Okay. Well, I'm a postdoc at Carleton working on the nEXO project under Razvan Gornia. Specifically, I'm on the barium tagging side, which is a proposed future upgrade to nEXO to increase its sensitivity, and I'm sure we'll get into more of that later. This is my second big postdoc, so I'm a little more experienced than a fresh graduate, but still have a lot to learn.
Awesome. Oh, happy to have you on the show. Happy to learn about nEXO and EXO. Before we get into that, though, let's talk a bit about your physics background. All right, so you started at the University of Manitoba, and you started in physics, right?
Yes.
And then you moved into your master's and your PhD. So what sort of physics did you end up focusing in or studying in?
I'm really into subatomic physics, so I can be divided into nuclear and particle physics, but I kind of like both of them. So depending on who you ask determines exactly what the projects I've worked on fall under. But so subatomic physics really covers it.
Okay. So you currently work on nEXO, which is the continuation of the EXO project, right?
Yes.
Yes.
It's a Neutrino-less double beta decay experiment.
Awesome.
Search for.
All right. We're going to come back to that. But first of all, you've worked on other stuff before that, right? You mentioned that you've worked on a few other things. Do you have any sort of, favorite project that you've worked on?
So I really like my PhD. So it was from the University of Manitoba, but the actual research happened at Triumph in Vancouver, which is a particle physics lab. They've got a big cyclotron there, and they have what's called the ISAC facility, where they make a bunch of rare isotopes. And so my PhD there was on trapping francium in a magneto-optical trap, which is a laser and magnetic field trap. And so we built this facility from an empty room to trapping a bunch of francium isotopes. And my part in that was to build the apparatus. And then we took some measurements of isotope shifts and hyperfine splittings, this and that. And then the broader experiment continued on and is still ongoing. So that's my PhD at the Triumph.
Yeah, wow. That's really interesting. What is kind of an application of the francium trapping, if I may ask? Like, is there any use for it? Is it coming towards some sort of experiment?
Yeah, so this is an atomic parity violation experiment. So when you do the math of dipole transitions between different levels in an atom, states of the same parity integrate to zero when you're doing your transition operator. And so those transitions just don't happen. You cannot go from an s orbital to an s orbital in a pure dipole electromagnetic transition. But the weak interaction violates parity. And you can exchange a Z boson between an electron and a nucleon in the nucleus, and that will mix your states of parity. So your s orbital is no longer purely s orbital, has a little bit of p characteristic. And so the s can go to that little bit of p characteristic, and then this transition happens at some very, very small amplitude, like 20 orders of magnitude below allowed transitions. And so by measuring this transition strain, you're really measuring the weak couplings between electrons and nucleons. And that gets you a hook into measuring something in the standard model, which will let us probe that sector. And if there's any disagreements between the standard model and what you're measuring, then that could be a hint towards some new physics. So that's why that's interesting. Yeah. The reason why you want to do this in francium is because francium is an alkali atom. It's the heaviest alkali. It's on that left-hand side of the periodic table at the very bottom.
Mhm.
So it has a very simple atomic structure. That's one valence electron, and then the rest of them's in the shell. So the atomic physics can be solved much more easily than more complicated systems. And it's also very heavy. It is the heaviest alkali. You have 200 and some nucleons in there. And atomic parity violation scales as the nuclear charge, roughly as the nuclear charge cubed. So as you go to heavier elements, your signal gets stronger, which makes it actually possible to measure it, which it would not be in something lighter like lithium. But the problem with francium is that it's only radioactive. There's no stable isotopes at all, so you have to kind of make it online and do your experiments, and then it decays away. That's why it had to happen at Triumph.
Wow, that is really cool.
Yeah,
So-
I remember that pretty well for having done it 8 years ago now.
Sounds like a really interesting experiment, though, and it's still ongoing, right? You said there's still people
Yes.
working on it. Wow.
Yeah, it's very hard. You need to really work down to that 20 orders of magnitude below allowed transmission amplitude. And so there's lots of intermediary steps where you measure something smaller as you improve your apparatus and build the next piece of kit that lets you get another 3 orders of magnitude down. And so it's just an ongoing process. And they're still working on it, and they're making good progress. I was just at a conference 2 weeks ago hearing the updates, and they've measured down another, like, I think 10 orders of magnitude since I was there. So they'll get there.
Yeah. Slowly but surely. That's really cool, though. And
Mhm.
so now you're working on EXO and nEXO.
Yes.
Would you mind explaining to our listeners what EXO and what nEXO are?
EXO is the Enriched Xenon Observatory. This is an experiment looking for neutrinoless double beta decay. So a double beta decay is when you have 2 nucleons or neutrons simultaneously decay to 2 protons in the nucleus, emitting 2 electrons and also 2 neutrinos. That's the allowed standard model channel. That one happens. And they measured it in nEXO 200, and it's it's 22, 10 to the 22 years is on the order of a half-life. So these things are very rare.
Mm-hmm.
What is proposed that can happen is you can have the same decay happen, but 0 neutrinos are emitted. The neutrino is virtually annihilated with the antineutrino that happens during the decay. This only works if the neutrino is a Majorana fermion instead of a Dirac fermion, which means that it's its own antiparticle. And so if you observe this thing, that is a direct indication of the nature of the neutrino, which is why people are looking for these things. They look them in xenon, they look in them in tellurium, in germanium, in different detector media. But EXO is looking for it in xenon, which is xenon 136 is the nucleus of interest, but it only has a natural abundance of about 10%. And so EXO enriches the xenon by various processes. And so instead of having a liquid xenon detector that is 10% of your target nucleus, it is something like 90% of your target nucleus. That's the goal, to enrich it. And so that just basically scales your detector up. Instead of having 10 times the volume for 10 times the signal, you just enrich it and get 10 times the signal with the same volume. But you have to take care to enrich your material before you put it in the detector.
Yeah. Yeah, I remember I went to Snow Labs 2 years ago, pre-COVID. And when we were there, we did a tour, and they were showing us one of the rooms that nEXO was proposed to be built in.
Yeah, in that cryo pit.
Yeah, in the cryo pit. And they talked about that they needed a few kilometers worth of tunnels connected to it just to build the machinery to enrich and produce all the xenon, if I remember correctly.
Yeah,
they needed
there's a
number of tunnels.
There's a lot of infrastructure that goes on to this, because liquid xenon is a cryogenic.
Mm-hmm.
And so they'll need to upgrade their liquid nitrogen capacity to provide the cooling to keep that cryostat at temperature. And so I think a big part of the infrastructure for Snow Lab upgrades in the near future is going to be the cryogenic capability to support these experiments.
Mm-hmm.
Yeah, Snow Lab's a very interesting place. A couple of years ago, I got to go down there too. That's our ride and a half down that mine shaft.
It is. It's quite interesting, actually, to thinking about the fact that now that you've gone about 2 kilometers under the ground, how many people have gone 2 kilometers below the Earth's surface? Not that
mostly
many.
just the people who mine it.
Yeah, all the people who mine down there.
And then that walk from the elevator to the entrance to the lab.
Mm-hmm.
That long, dark tunnel.
It's a hike.
Yeah.
For the listeners who don't know, Snow Labs is a physics laboratory in Sudbury, Canada, which is built, well, it's attached to a current active mine shaft. And it's built off of the location of the snow experiment, which won the Nobel Prize back in, I think, 2012, 2010?
Something like that. I don't remember the exact year.
Yeah.
It was 2012.
And now it's a big facility.
It's a world-class facility, and it's got lots of interesting physics going on there.
Yeah. They've got dark matter detectors. They've got Snow Plus. Well, there's is nEXO being built at Snow Labs, or
there's still approvals to secure funding before any of these next generation ton scale neutrino beta decay searches are built. So it's still in the approval process, and us and other experiments are interested in that space.
Well, best of luck for nEXO getting the space down there.
But they can accommodate more than one experiment there. It's just if they take both of us, then all the other experiments that want the space that are not neutrinoless double beta decay are going to be a little disappointed.
Mm-hmm. Oh yeah, it's always unfortunate to not be able to get the space that you're looking for, but there's only so much room for now.
Yeah, and Snow Lab is like the #1 location for this. They have kind of the best facilities and the best overburden is what it's called. The shielding factor of the rock and intervening material between us and the surface to shield from cosmic rays is like snow is #1.
Mm-hmm. Actually, would you mind explaining why the shielding is so important for this sort of experiment?
So these experiments looking for these rare decays, the limits on the current limit on the half-life for neutrinoless double beta decay in xenon 136 is something like 2 times 10 to the 24 years. So with such a long half-life, you need massive amounts of material to look for the decay in, which is why we're now going into these ton scale experiments. But with such large detectors and such large volumes and all the enclosing apparatus and shields and this and that, you need to take great care to very control your backgrounds and reduce them as much as you can, and being able to discriminate background events versus decay events. Because if your detector has a background of a few events a year, that's potentially 10 times larger than your signal, and trying to determine the signal out of the background is just wouldn't work. So you take great care to choose all your detector materials to eliminate all the sources of background. But the biggest thing that you can't really avoid in detector construction is activation of the detector material by cosmic rays. So a muon comes in from the atmosphere, bombs into your detector, scatters off some nucleus, and that nucleus is activated. It will bomb off a nucleus, shatter it, releases some neutrons, and some other nearby nucleus absorbs a neutron. Then that guy's now radioactive. And like xenon 137 will beta decay, and that could be confused as a double beta decay event if you get unlucky and you can't discriminate it against a real decay. And the only way to really get away from cosmic rays is to go deep underground, have sufficient material between yourself and the sky that these high energy particles have scattered off something between you and the sky so that it doesn't make it to your detector. And so by going deep underground in Snow Lab, you like reduce by orders of magnitude this source of background. So the only way these experiments would ever work is if you can get them deep underground.
That makes complete sense. It's important to have that shielding to remove all the background noise. Right. So
this main source of background, there's still lots of other ones that nEXO has made some very clever design choices to do this.
I'm a bit aware of background noises. I did a bit of work with Simone during my second year. I got the Dean Summer Research Internship, and my job was to deal with noise from alpha decay in the neck of the deep detector that looked like they looked like actual dark matter events, and they weren't. because they were outside of the area that the ball appeared in.
So
like a
right,
big
that's the same idea. You've got decays happening where you don't want them to happen, and you got to make all your choices to reduce them as much as possible, and then train up your detection algorithms and all that to be able to discriminate what remains.
Mm-hmm. Because we want to know, we don't want to accidentally detect something that isn't actually there.
Exactly. And with these such rare decays where you've got data collection going on for 5 or 10 years of these ton scale detectors, that just to be able to find the potentially, 5 events that'll happen over the lifetime of the experiment, if you've got one that is not real and you can't tell it it's not real, that's a bad news.
Okay, so you are focused on working on barium tagging.
Yes.
Right. So would you mind explaining what that is, why it's important?
So when your xenon 136 decays and spits off 2 electrons, you follow your periodic table, 2 spaces over is barium.
Mm-hmm.
So for every xenon 136 decay, whether that's by the allowed double beta decay with 2 neutrinos or the searched for 0 neutrino version, it always produces a barium 136. If you could detect a barium 136 at the position of this decay, nEXO has a time projection chamber, which will pinpoint the location where this decay happened. If you could detect the barium 136 in that location, then you can be sure that this was a double beta decay and not something else, not like a xenon 137 single beta decay that just happened to look like it because of some detector inefficiencies or whatever. Then that eliminates all backgrounds other than the 2 neutrino version of the double beta decay. And so all those things like cosmic rays and radon from being underground in Snow Lab, all those other sources of background are just completely eliminated if you have 100% detection efficiency of this barium daughter. But that still leaves you the problem of finding a single atom or ion inside a 5-ton volume of liquid xenon.
Mm-hmm.
And so we're exploring various ways to do this. Here in Canada, we've got one scheme. We're working on this. Carleton and I are working on the actual fishing out of the ion, getting it from that decay location into another chamber where all of the rest of the detection and identification apparatus is. We've got colleagues at McGill working on our funnels to separate the ion from the xenon that will come with it, and then a Paul trap to do some spectroscopy on it to identify that was barium, and then a time of flight mass spectrometer to determine that it was barium 136. So it's a complicated scheme that's been broken down into chunks, and here at Carleton we're working on the extraction side. We've got colleagues in the States working on different methods, cryogenic probes where you'll freeze the ion into a little bit of xenon ice to move that to where you can do some spectroscopy on it. Others are working on electrostatic probes with the same idea, where you attract it with an electromagnetic field onto the surface of a probe to move it around where you can do some identification. And so this is an active area of research that we're very interested in, because if you can detect the barium with 100% efficiency, that gets you something like a factor of 3 higher sensitivity for the same detector. So that's big motivation, because then instead of having a 5-ton enriched xenon detector, you're punching at a 15-ton xenon detector equivalent.
Yeah. So you said that at Carleton they're focusing on the fishing method.
Yes.
So I don't know how much you're allowed to say, but how are they kind of looking towards doing that? Like, how are they thinking about how to fish it out, I guess?
Yeah, so this is what I'm actively working on. We have we've done some simulations showing that with a capillary and the pressure difference between the inside of your cryostat, which you operate at, say, 1.5 bars of liquid xenon, and a detector chamber at something lower than that, the suction of this capillary should maintain flow conditions such that the ion will move through the capillary without touching the walls. If it touches the walls, then your ion can be neutralized and then lost, because the detecting scheme relies on it being charged to separate it and load it into the Paul trap and all that. So we think we can do this with a capillary.
Okay.
And so we're aiming to demonstrate that. That's the research we're doing.
So to demonstrate it, are they physically designing something at Carleton, or is it all currently just simulations and Monte Carlo?
During work from home, it was all simulations.
Yeah.
But we do have the nEXO 100 GPC. So this is 2 generations ago, the nEXO experiment. So we've got its time projection chamber and the cryostat here. So we have the apparatus that we can do a decay measurement. And so we'll load some radioactive into the xenon, observe its decay, bring the capillary into position, suck it out, and detect in coincidence the decay in a separate chamber. And if the energies of the decay match, then we can say it was the particle that decayed in the cryostat is now decaying in this other chamber. Then we can conclude that we successfully extracted the daughter. And so that's the idea. That's what we're working on.
Really interesting.
There's lots of other little jobs about it too. So not only do we have to get this capillary working, but how do you move it around? You want to be able to get it to sufficiently accurate position. Instructions in the way, because your time projecting chamber is basically a can. So how do you get a capillary through a can? We have some little holes in the can, but we need to be sure that we're coming through the holes and not driving the capillary into the 8 kilovolt cathode, for example. So there's lots of I guess kind of like robotic control involved that wasn't expecting initially, but we determined we will need the precision of the precision and speed of a robotic controlled system to automate the whole process from once you detect a decay to getting the probe into position. We have a master's student working on this displacement device, which is kind of looks like a little bit like a 3D printer to swing this probe tip around.
So is the probe tip then directly in the detector itself?
Yes.
Okay.
Yes. So that will be inside the cryostat. So at 165 Kelvin, 1.5 bars of liquid xenon, this guy gets moved around.
Oh, that's fascinating. Since we're coming near the end of our time, I'm going to ask you the question that I ask everybody. What do you think has been the most impactful physics experience that you've had as someone who's studied it, become a postdoc now, and is heading into, I'm assuming you're heading towards potentially getting tenure or something like that. So what are you?
I have to find a faculty position first, but
yes.
I think my most impactful physics event was my first postdoc was on the alpha experiment, which is anti-hydrogen spectroscopy over at CERN. And I was working on the side, working towards laser cooling this anti-hydrogen, because if you cool it down, then all your spectroscopy works better because you have narrower line shapes and less Doppler shifts and things like that. And it was a lot of work getting this thing going because hydrogen has that famous 121 nanometer transition energy from the 1s to the 2p. And this is not an easy wavelength to generate, and aligning it. So it has to be all in a vacuum, and aligning through vacuum is a total nightmare. And so there was lots of work to get this thing going. And so finally, at the end, at the beam time that year when we were trying this, and finally seeing this thing work, where all of a sudden, after 8 hours of taking data on that run day, getting the analysis going and seeing that, oh look, the energy spectrum has cooled down and this is finally working. That was just such a moment of pride and relief that this thing worked. And then the very next week, guys working on the spectroscopy side used this to take a better measurement of their spectrum. And so it was just great that this was like a new paradigm of anti-hydrogen physics that I contributed greatly to. So that was my best moment.
That's amazing. Well, thank you very much for coming on the show, Rob. It's been really enlightening to hear about your experience as a physicist and also all of your work that you've been doing, including especially nEXO and nEXO. I know that we kind of focused on that.
It's the current one I'm working on, so I'm happy to talk about that.
Awesome. Well, best of luck with your research.
Thank you.
I hope nEXO gets all the funding that it needs to go through. And again, it was a pleasure to have you on the show.
Yeah, happy to be here.
Thank you for listening to this episode of The Quantum Mic. Big thank you to Dr. Robert Collister for coming on the show. Join us next month for another great episode. You can follow The Quantum Mic on Twitter at quantum_mic to stay up to date with the show, and let us know how we did by leaving a review and subscribing. If you'd like to come on the show and talk about your amazing research, you can email us at thequantummic@gmail.com. This episode of The Quantum Mic was hosted and produced and edited by Owen Dara. Quantum Mic Podcast was created by Owen Dara, and the music used in this episode is by Kevin MacLeod. Thank you for listening, and we'll hear you next time on The Quantum Mic.